I wanted we start with describing what memory is, because once you understand memory, then you'll understand how functions are called natively and how to create memory natively, and how memory actually affects your application in terms of the capability it can do in terms of utilizing the hardware you're running your application with. And it all starts with memory. Memory is just the storage of data in your computer, but how it is described structurally is what many people don't usually have a grasp in terms of understanding the concept. And also Java tends to hide the information of how the layout is done. So most programmers in Java tend not to have that knowledge. And that's the case that happened to me. I started with Java, but later on I discovered that understanding memory layout is very important. Even other languages, even C, hides memory representation in terms of not giving the user information on how data is structured, but it has some specification of how it generates the layouts. So C is very good at, has a standard way of actually displaying layouts, and it's what C++ adopted. I don't know about C#, but most modern languages nowadays, they hide the layout because they want to have that freedom of rearranging how the layouts are represented in memory. And it's why most modern languages, you see the way to interface with them is through a C API. So C API nowadays has become the de facto of interfacing between different programming languages. And it's because it has well-defined memory layout. Okay, so we begin there. So here, as you see, it's memory representation and typed memory. And then down there is mapping product types to native memory. I believe you understand what product types are, but I'll explain further, but briefly. So we start with memory layout. I've actually presented this before, but it's good to have a reminder of what it is, and also I'll describe the rules. The rules can actually fit in one page, I think six lines, so that you understand the rules of memory alignment, memory layout. So memory layout, it's like a schema. So if you guys have done serialization, marshalling, you transmit data in binary form or through the wire, you tend to create a schema first. I think frameworks like GPRC, they tend to have a schema layout, and it's the same concept in a way. So difference between schema and layout. Layout is more like a shape. So shape is more like you say int. This field is based on int, and then float. But schema, they usually have added information like the name of those fields and maybe the validation for that layout itself. But that's a digression. So how pure data structures are organized in memory for system languages. So by the definition of system languages is quite difficult to say, because people usually talk about system languages, but there's no standard definition. But when you hear people talk about system languages, it's all about memory. So arrangement of fields is in contiguous memory. So it's like your keyboard, the way the keys are arranged. There's no space in between. So that's what we call contiguous memory. And then it's governed by alignment and padding rules. Alignment is based on hardware specification. Padding rules, I'll explain later what it is. And each field is placed at a properly aligned offset. If you notice clearly here, this statement means order. If you say, if your class has field X, Y, and Z, that's the order. But in memory, that's defined by the offset, where this Y starts, where this Z starts. But Java fields don't actually promise you that the fields will be aligned the way you define them when in syntax form. That's one of the reason why records came, and then later on in future we'll have carrier classes. And then the padding itself is done automatically by the compiler, but Java Panama decided to make everything explicit. It's for the programmer to do that manually. So, and the reason is that they don't want to trap themselves in adding padding or providing a layout approach based on each operating system and hardware. So it's for the user to develop that framework. Actually, if you notice, since 2010, Java has tried to make everything explicit so that developers can develop libraries. Even the way the language is going forward, they'll give you the basics, and it's for you to develop a complex library on top of that. And Panama actually was designed that way. And then the overall structure depends on alignment requirements and actually alignment requirements. So this matters a lot. For example, performance and cache efficiency. Cache efficiency is everything. Actually, when people I've seen these fights on Twitter. So when people say Java memory model is the worst memory model out there, because what they are saying is that it doesn't have this cache efficiency, and I'll explain later what it is. And then native interoperability. As I said, if you notice Zig, Odin, even Jai, and then Rust, all those new languages, they use C for native interoperability, same as Java. And then serialization and memory mapping. Actually, my library is a form of serialization, if you think about it. And then memory mapping, and then systems and high performance programming. Yeah, so that's the case. So if you look at every language, just Google what their basic primitive types are. Every language has its own primitive types. Rust has a lot. Java has these main ones. Because you cannot they can never include all types of primitives in a language, so they usually provide the basic primitives so that you can build complex primitives on top of that. But Java, you cannot construct complex primitives on top of that, but soon that will change. But you need to understand their memory size. So for example, a byte is digit 1 in terms of bytes. Char is 2 bytes, but in C is 1 byte. So if you are unaware of this, you'll encounter a lot of memory conflicts when you are mapping your code like a string to C string. So most C strings are usually represented as bytes in Java. And then short is 2 bytes, int is 4 bytes, float and 4 bytes. If you notice int and float, they usually have methods called to float or to int. It's because they're interchangeable in terms of memory representation. It's the same memory size. So you can apply rules to present a float in an int, and I think vice versa, as long as you have native memory access. But Java provides a way of doing bit manipulation so that you can be able to interchange. And then long and double, same concept. Beyond these values, these sizes, you now enter a different area called single instruction multiple data. That's usually more hardware specific. So that's usually out of scope for all programming languages. I think so. Yeah. If you want to go beyond that, you look for libraries providing such a kind of access. But in future, we'll be able to model this. I think so. And then Java soon will introduce Vector API. Actually, they are waiting for value classes so that they can go beyond these primitive types that are target specific hardware. But you can also define your own primitive types. Also, the unique thing about primitive types is that they don't have an identity, which is very crucial. I'll explain later. So in C, this is a product type. So a product type has multiple fields. The reason why it's called product types is that if you count all the numbers that can be represented by maybe X, and then you multiply also by Y, by Z, you get all the possible values this struct can have. That's why it's a product type. And most languages are that way. And actually, the way you can prove that is maybe turn them to Boolean, because it's 010101. You can actually see the different ways you can represent that data. And it has a formula, I think 2 power n. So for Boolean types, 2 power 3, that's I think 9 ways of presenting that data based on the Boolean types inside. But here it has, I think, billions, or I think so. I've forgotten the value. So in terms of how they are represented in memory, as you can see, these are offsets like 0. Let's imagine this is the point in a struct. So it starts with 0, x, and then since it's 4 bytes, you add 4 bytes. So the next one starts at index 4, and then 8, and then 12. So you can say the total size of this point is 12 bytes, and it's based on the size of each field based on the types. So the type is very important. But once you by now, I think everyone knows the size of each primitive. So it's usually offered, but it's important to know. So for this, it's just 12 bytes. So some people can see a struct and then they know these are 12 bytes or 24 bytes etc. But there's some situation where a language might introduce some sort of padding in between in terms of product type representation in memory. So, for example, you remember char in C is 1 byte. So if it starts at index 0, it's 1 byte, but it has to add 3 bytes so that it starts at 4, and then Y is 4 bytes, 8. You notice something? It's in the power of 2 actually. It's divisible by 4, or by the size of that field. For example, Y is size 4, so it has to start at index 4. And then Z is size 4, so it has to start at 8. So there's that rule you have to think about. But most programming languages, the compiler does that for you, so you don't have to think much about that. So so the right side explains the padding etc. So the alignment requirements depends on the language and also the hardware. In Rust, this information is not accessible. It's not currently a standard anywhere. So the compiler has the freedom to rearrange this, and I'll explain you why rearranging is important. And also the value classes in Java will take this approach too. So even complex paddings exist. So for example, this struct has char C, that's 1 byte. Int is 2 integers inside, so because it's an array, so it's 2 ints inside. So they're well padded. There's no padding in arrays. I'll explain why there are no paddings inside an array. So for example, C starts at 0, so 1 byte, but since the next field is an int array, and the first each element size is 4 bytes, so it has to be a multiple of 4. And then since 4, okay, this is 4, and then 8 plus 4, 12. The next one is double, which is 8 bytes. Here it's index 12, but 12 is not divisible by 8. So it has to pad more. So it adds 4 bytes, so 16. So it's a multiple of 8, and then the total size is 24. So this is how C does its memory alignment in terms of product types or structs. So these are the rules, and I think there are seven rules actually. So each field is placed at the next offset, satisfying its alignment requirement. So alignment is usually a power of 2. And then the compiler inserts internal padding between fields when needed. And then there are some situation, for example, let's take this V is a double, the array is an int, so it is divisible by 444, so there'll be no padding, and then after it, there's a char. So this is 8, and then plus 8 is 16, and then since the C is a char 1 byte, so it will be 17, but it adds 7 bytes. But the question is why? So in this fourth line, it says Kmax is equals to the largest alignment required by any field in the struct. So if you look at this struct, the largest single field is 8 bytes. So the last padding, the last offset should be divisible by the largest field size, which is a double. So it's an 8. So it will add 7 bytes, so that total is 24. So this is a multiple of 8. So with these rules, that's why arrays don't have any padding, because the struct inside obeys the alignment through offsets and padding. Therefore, you can never think about having padding in arrays, because arrays will never have paddings. So that's the principle. Before I understood this, it took me time, like almost 2 months. I didn't know the rules. I didn't know until I discovered a library on GitHub, and I was able to go through each line, and then I found a certain formula, and then that's how I discovered those kind of rules. And this one came from a Stanford University presentation, so I was able to use that. But it's so strange. There's no publication or a specification highlighting this, so it's quite strange. But once you understand that, things start making sense. So, for example, why order matters. So, for example, if struct S1, this one, actually this struct is the one we are going to use throughout this presentation, because I think it shows some bit of complexity, which is good once we start now thinking about Java. So struct S1 is the 3 fields. The first one is a char, and then the other one is an int, and then the other one is a char. So this is CID. So the first one is 1 byte, so it has to pad 3 bytes, and then I, which is 4 bytes, and then D, which is a char, is 1 byte, so it has to pad 3 bytes, total of 12 bytes. But notice the order reduces the size to 8 bytes if you start from the biggest to the smallest. That's why if you give the compiler freedom to rearrange the fields, it brings a lot of memory optimization. That's what Rust does. I don't know whether Zig does that, but value classes also in Java will do this. Yeah, so this is about memory optimization completely. So, but sometimes order has no benefit. Even if you start from the largest field to the smallest field, sometimes you don't gain anything. But it's good to be safe, on the safe side, always arranging the largest fields all the way to the smallest fields. So after this presentation and today's a meeting, just go to GitHub and look for C code anywhere, and you'll notice how people arrange their fields. You'll notice that order of fields. Some people don't really care, but for game developers, this is very important. For high performance computing, this is very important. And then notice something, in Java, arrays are usually objects with identity, but in C, if you declare it this way, it has no identity. It is stack allocated. So it actually affects performance. And when I decided to do this in my library, I noticed some overhead, whereby my performance of my library wasn't in par compared with other languages. But I think Java, they are planning to introduce stack allocated arrays. They are called multi-field array, but it hasn't been made yet publicly, but it has been discussed on Reddit and I think in the mailing list. So once you have that, you don't think about array layouts. Arrays just, each struct is ordered very well. They don't have to think about padding everything, etc. So let's enter Java Object Memory model. So there was a time I was making a user interface and I was dealing with Java beans, so I wanted to inspect them in terms of through reflection. And that's when I stumbled that issue that actually fields in classes are never ordered based on how you write them, because the reason is they are not even stated in the specification actually. So they are never declared anywhere in the specification. So different JVM implementation, they might obey the order or not, but it's not a guarantee. So the problem with Java object is that they have a pointer and then the pointer points to the actual data, and I'll explain why that brings an issue. So this memory model results to many cache misses, slowing reads and writes. Actually, this is, if you hear about Java is slow, this is the reason. This is what they're trying to fix. Even today on, let me share something. Even today on, this is the trending topic in Hacker News. Yeah, it has gone down. Yes, it's number 2. Project. Someone gave a very detailed article. Look at those comments. 242. So this guy just gave the history of value classes in Java. So, but this is now people are encountering this new model, which if you go through the comments, some people are misinformed, some people quite impressed. Some people are quite confused. It's an interesting paradigm shift we are experiencing right now. But the reason is they are trying to fix this line. The memory model results to many cache misses, slowing down the reads and writes. And I'll explain how that happens. So both languages, system languages, as they say, Rust, Go. I don't know whether Go is a system language. Zig, C#, which has structs. They were able to actually avoid the object model whereby a data has a reference, which slows down access to the actual data through reads and writes. So the reason is that in the beginning, in 1995, I think when Java came out, there was no issue of difference in performance between memory access and CPU instruction execution, but later on, CPU's architectures improved and they introduced redundancy memory hierarchies called cache slots. So so usually have the SSD, but do you know virtual threads? To switch from one virtual thread to the other, the first test they can do is, I think, 90 nanoseconds. And accessing data from SSD drive is around, I think, 100 microseconds. So when you hear that they haven't figured it out on how to do proper I/O in files, it's because the switching context between one virtual thread to the other during blocking while reading a file from the SSD drive, there's no performance difference. So that's why most I/O in Java using virtual threads, they block the carrier threads. Yeah, it's because of memory access actually. So SSD drive is 0.1 milliseconds. Main memory, the RAM, you say at my computer 64 gigabytes of RAM. So it's 62.9 nanoseconds. Now, this is the most interesting part. So the L4 cache for 42.4, L3 cache 12.8, L2, L1, and then registers. Registers is a different beast of memory access. It's where the CPU will try to obtain data from this memory hierarchy and then store them in the register and then now do the instruction execution. The most languages actually through assembly language. If you ever follow FFmpeg, they do assembly programming. if you look how they code, they usually go through straight to the registers. They don't deal with cache 1, L1, cache L2. That's why they usually say assembly. If any language ever beats assembly, that's a lie. Because it's a register access. But if you look carefully, I think, I don't know whether I have CPUs. Nice. I do. I still do. So as it opens, here. So I don't know whether it can display the cache size of my. Oh yeah, it is. So if you look at here, L1 data size. So there's L1. The cache is level 3, level 2, and then level 1. So each has its own memory size. Like a level 3 mine, it's 24 megabytes. Level 2 has lower megabytes, etc. If you can fit your data into this L3, L2, L1 cache, it means you have access to very fast memory access. That's why arrays are very common, or multi structs which have multiple fields. The way they align memory in their types, it's very important. So if, let's say, this struct can fit in this L1, the access becomes fast. But if you read an index in an array, the CPU will read that index and also the data surrounding the other indices, so that if you're going to call the next index, it won't go all the way to the SSD or main memory. It will just go to the L1 cache. That's why it makes things very fast for modern memory access in terms of accessing computation speed and also access of memory. So the idea is to flatten memory as much as possible so that they can fit in these slots. And the future value classes will take this advantage, whereby these fields will be dismantled completely and then stored in the registers. That's why Java never allows you to have access to the memory layout, so that it has that flexibility to do garbage collection. But now the new value classes, you'll be able to access. Java will be able to access data, stored data in the registers instead of L3, L2, L4 cache. So it will be super fast. That's why I'm actually wondering how benchmarks in future will be comparing Java and Rust. So what happens when there's a cache miss? Because as I said, Java experiences a lot of cache miss. So the concept of cache miss is that the CPU requests data. For example, let's say in the beginning, when your program starts, you request data in a certain address. So when it reaches here, it will fetch a 64-byte line. It doesn't depend on the size of your data or each type. It will always collect 64 bytes of memory, so that if, let's say, it's an int, and an int has 4 bytes, so it means this is how many? I think, is it 18 or whatever? It will read many indices in that array and store them in the cache. So once you request data, a whole bunch of data will be stored in the cache. And then if it requests again the next index, it will look first in the cache and say, wait a minute, the data is already, the next data in the maybe index 1 after reading 0, it's already in the cache. So it will process first and then return. That we call a cache miss, a cache hit. But if it reads index 1 after reading index 0, it becomes a cache miss, and then it has to go back to the RAM. So, and then now go back to cache and then go back to CPU. You see that latency of reading data from the main memory. So that's the issue. So that's, unfortunately, that's how the Java memory model is because in an array, as I had mentioned previously, in C, they store the actual data, but in Java, if you store objects in an array, they don't store actual data in the array. They just store references to that data in the array. So when the when the CPU reads the data from maybe index 0, it actually reads notices, oh, this is a pointer pointing to a data in a different memory area. So it will it will read a whole bunch of reference first, and then it might even read maybe depending on how the data is stored, it might actually store some data in the cache actually here. And then if it reads the reference, and then it will know, oh, the reference points to the actual data somewhere. And if it's in the cache, that's it's supposed to be a cache hit here. If it finds it, that's good. But since it's not the actual data, it will always point to a different location. We encounter a lot of cache miss. So that's why many years have gone where CPUs have improved memory access, but Java hasn't adapted to that memory access architecture of modern CPUs. And the reason, and that time, people usually say Java does a lot of pointer chasing, so it has to go so many corners before it get actual data. So that's the reason. And if you look at there is this poor spatial locality that is not well grouped for me to search around the memory neighborhood for the actual data. So it has poor spatial locality in memory. So which increases cache miss probability. And then this leads to high memory access latency. So, sorry. So yeah, so at least now you understand the reason of why memory layouts are important. But as Java developers, we don't have this kind of information. We tend to trust the JVM to do much of the work for us and to optimize as much area as possible. But unfortunately, optimization has limits. So the best way to tackle that problem is to remove references and store the actual data contiguously in memory. And arrays are the best way of storing the information contiguously in memory. So having C arrays in C, they're quite efficient because of that. And Valhalla also wants to deal with that access. So for here, if you want to read, it reads this whole 64 bytes all at once and stores them in the cache. So if I read 0, yes, it's in the cache. If I read index 1, it's already in the cache. If I do that, that's the beauty of cache. So when you're buying CPU, always think about your cache memory, and you can check in your computer. Download CPU-Z, it's free online. It gives you access to your hardware specification. So in future, Java will do the flattening. So instead of pointers, the headers, every object has a header and then the data itself. In an array, it's the header and then references to those headers. So reference. I think reference is 32 bytes. 32 bit, sorry. 32 bit, the reason is because in 1995, most CPU architecture was 32 bit, and it has never changed actually. So references, you can use actually, what do you call it? You can use the GTorch, I think, and what else? There are some tools you can use actually to check how memory layout is done in Java. So this is a lot of pointer chasing. That's why you'll see this kind of diagram when you read about memory in Java. So now you understand the concept why. So in future they're going to remove these headers. So in an array, it will be short. So it will be the same based on how it's going to be arranged contiguously, and then this will enhance a lot of cache locality, reducing cache misses. And notice something here. This is a Java array, but if you zoom carefully, there's a null restricted type. I'll explain why. Yeah, that's a giveaway or something you'll see. So the reason why is that the current Java value classes, they will have null marker. So you might think it's short X, short Y, short Z. No, it will also have a null marker. So some people are testing value classes in Java and then they discover it's not fast. It's because beyond 64-bit, it becomes a Java object, an ordinary Java object with pointer chasing. So in future, once we have null restricted types, this null marker will be removed, and then there'll be header, short X, short Y. Right now, this is how Java arranges memory with value classes. Most people will notice there'll be no speed, but the reason why they're introducing value classes is because they now have a way of now removing identity. After I think Java 28, that's when they'll start now doing proper optimization of Java, and then JEP, like I think JEP 4.2 or what, they'll introduce null restricted types. So once they introduce null restricted types, these null markers will be removed, and then also the 64-bit whatever. So at least now you understand memory layout. Actually, what I've described, I hope rewires the way you think about memory handling in other language. You have to think about, do they flatten their memory? Do they introduce value structs or value types, value objects, like in Odin, in C, even C#. C# has both. It has structs and also ordinary class objects. So, but the approach was quite interesting with some traps, which they tried to resolve later. But now you have an idea. If you now go research other programming languages, go with that mentality of how is memory laid out for a given type, which has multiple fields. Always have that idea, and how is it represented in an array? Then you'll understand why it's very important. So, and the beauty about that is that you can predict memory size, actually. Yeah, so if I have an array that has 1,000 elements, it's possible actually to calculate the memory size of that array, so that you understand this system hardware I have. What strategy should I take? For example, when you're programming your phone, you're programming your watch, etc. Memory is very crucial to such systems. That's why it's very hard to find Java being used for system languages as a system language.